Hello, welcome to Econometrics Melody. In this video, we'll discuss about the special random variables, and let us see it once again through the example of tossing two dice. We have already seen this example in our previous video of random variables. So when we toss two dice, we make the list of all the possible events or outcomes, and then we create a random variable. Let us say it x, and here the random variable is the sum of the numbers appearing when we roll the two dice. So these are the list of all the possible sums, and we assign their respective frequency, and we calculate their probability as well. So the sum of the probability is equals to 1. So this random variable x, when we plot the probability against this random variable, then we see that a certain distribution emerges out of this experiment. So generally this distribution is assigned with the population. That is, we assume that a population has a certain distribution, and we calculate the sampling out of it, and we carry out the test or the desired test. Generally this is a theoretical distribution, and the distribution is attributed to the population. And assuming that the population has a certain distribution, we apply certain sampling techniques or sampling procedures, and based on the statistics of that sample, we infer the characteristics of the population. These are the topics we are going to cover in our forthcoming videos. Now up to this point, we are clear that from a certain random experiment, we can create random variables, and that random variables follows a certain distribution like the one discussed here. This indicates some sort of normal distribution. Based on the nature of the random variable, whether it is a discrete random variable or continuous random variable, we get their probability mass function if it is a discrete random variable, and we get their probability density function if it is a continuous random variable, as well as we can construct the cumulative distributive function of the random variable. Now up to this point, we are certain that a random variable, whether it is continuous random variable or discrete random variable, it has a certain distribution, and these distributions can be defined in some sort of functions. And when we have this function, we can calculate the mean or standard deviation or the moments of these random variables. Now in today's video, we are going to discuss about some special random variables, and we are going to name them, and we are going to name their distribution as well. So these are the lists of the special random variables and the distribution, along with some properties, as well as the hypothesis testing for these different kind of special random distributions or random variables we have covered in our earlier videos. So let me show them. So we have already covered about binomial distribution or the random variable that follows binomial distribution, negative binomial distribution, hypergeometric distribution, Poisson distribution, exponential distribution, and Laplace distribution, normal or Gaussian distribution, and Z statistics out of this normal distribution, and inverse Gaussian, or which is also called as the Wald distribution, gamma distribution, chi-square distribution, and student's t distribution, beta distribution, Fisher-Snedecor distribution, EF distribution, Cauchy or Lorentz distribution, logistic distribution, and Weibull or proportional distribution. Please refer to these videos for the detailed understanding on particular topic. Now in today's video, we are going to calculate the mean and expected value if the variable we are considering is a Bernoulli random variable. Now let us say an example. So if our experiment has only two outcomes, maybe if we can distinguish the outcomes or the events into two distinct parts or two mutually exclusive parts, is success or failure, either it is yes or no. If the outcomes are distinct and limited into two mutually exclusive parts, then that is called as the Bernoulli random variable. And in that case, let us represent the random variable, Bernoulli random variable, by x, and let us indicate the success as 1 and the failure is 0, and the probability of getting success represented by p, and the probability of failure is represented by 1 minus p. So the sum of probability should ultimately be equal to 1. So from this relationship, let us calculate its x square if we happen to calculate it. So this is again 1 0, and if we want to calculate x cubed, this will also be equal to 1 0, and if we want to calculate accordingly, if we want to calculate x to the power 1 n, that should also be equal to 1 0. This does not change. So this is again a discrete random variable because the variable is accepting, or the variable is taking the discrete values or the counting numbers as its values. So whether it is a discrete random variable or continuous random variable, we have already seen that we can calculate its expected value for the first moment as well as its variance. Now let us calculate the expected value and variance of this Bernoulli random variable. We know that. Let us expand this in this case. Therefore, the first moment or the expected value of a Bernoulli random variable is equal to the probability of success. Now we have already seen that the value of x, this is equal to x squared, x cubed, and so on for this special case. Therefore, if the expectation of x is equal to p, expectation of x to the power n is also equal to p. It is quite obvious. As for example, if we want to calculate the expectation of x squared, the value of x does not change, so this is also equal to 1 into p plus 0 into 1 minus p, and the result is p itself. Now, by the help of this result, let us calculate the variance of the Bernoulli random variable x. We know the formula to calculate the variance. This is equal to, and we have just seen that expectation of x squared is also equal to p minus expectation x is also equal to p and its square. So this is equal to p minus p square, and if we take p as common, we are left with 1 minus p. This is the variance of the Bernoulli random variable x. So the product of the probability of success and failure that gives the variance, while the probability of success is the expected value for the Bernoulli random variable. So we know this result, we have just proved this, or we have calculated it, or we have derived it. Now let y is equals to x squared. So we can write x cubed is x into x square. So this is equal to x into x square is our y. So expectation of x cubed, this can be written as expectation of x is x itself and y is x square. X is in fact our Bernoulli random variable, therefore y is also a random variable because y is the function of x. If x is our random variable, then y is also our random variable by construct. Now we want to see whether x and y, they are independent or not, and we know that in case of the independent events x and y, then in that case the product of their probabilities should be equal to the probability of their intersection, and the expectation counterpart, this should exhibit this relationship. And we want to check whether this is true or not for the x and y that we have supposed. Let us for the time being assume that x and y are independent, and we want to see whether this relationship holds true or not. So if they are independent, then the expectation of the product should be equal to the product of the expectation. The expectation of x, in case of Bernoulli random variable, it is p, and expectation of y, this is equal to expectation of y is x square, and this is equal to p into expectation of x square is also equal to p. We have already seen this. This should be equal to p square. So if x and y are independent, then we should get that the value of expectation of x cubed should be equal to p square, which is not true. Expectation of x cubed is not equal to p square, but we have seen that expectation of x or expectation of any power to the x, that is equal to p. So we say that x and x square, they are not independent because x and x square, they failed to exhibit this property of expectation, that is the expectation of the product was not equal to the product of their individual expectation. So this is how we test whether the two random variables are independent or not. In this case, x and x square are not independent. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.